Hello everyone, welcome to the class. Today we will discuss about the design of Chebyshev filters. There are two types of Chebyshev filters. One is type 1 and type 2 type of Chebyshev filters. Type 1 Chebyshev filters exhibit equiripple behavior in the passband, whereas type 2 Chebyshev filters exhibit monotonic behavior in the passband. Whereas type 1 Chebyshev filters exhibit monotonic behavior in the stopband, and type 2 Chebyshev filters exhibit equiripple behavior in the stopband. So that's how they are different from each other. And also type 1 Chebyshev filters are all pole filters, whereas type 2 Chebyshev filters contain both poles and zeros. And the zeros of this class of filters lie on the imaginary axis in the S-plane. We will see in detail about the pole location and the zero location in the coming slides. Now we know that the frequency response of a Butterworth filter is maximally flat in the passband and is monotonically decreasing. So that means that this is this is maximally flat in the passband and it's monotonically decreasing. Type 1 Chebyshev filters have ripples in the passband and monotonic in the stopband. Type 2 Chebyshev filters are monotonic in the passband and ripples in the stopband. And elliptic type of filters are the optimum filters having very small transition width. Now, if you do not include elliptic filters in the category of in the design of filters, then Chebyshev filters are next optimum filters to the elliptic filters in terms of the transition width and sharpness of the filter. And now, if you also see what is equiripple behavior, equiripple behavior means the ripples in the passband, the amplitude of the ripples, the positive amplitude and the negative amplitude, they are both same. That means the maxima and the minima values are same. The distance from the axis. All right. So therefore, these ripples are, as I mentioned here, also equiripple behavior. So therefore, we say that the Chebyshev filters exhibit equiripple behavior either in the passband for type 1 and or equiripple behavior in the stopband for type 2. Okay. So now let us discuss the squared magnitude. Now this equation is for the squared magnitude response of a type 1 low pass Chebyshev filter. We also know that to design the Butterworth filters, we started with the low pass filter prototype and then we used the transformations to convert a low pass filter prototype to other types of filters like high pass, band pass filter or band stop filters. The same strategy we will use for the Chebyshev filters also. We will consider the type 1 low pass filter design first, and then we will take the design maybe to design further for high pass, band pass or band stop filters. We can take that same strategy forward. And one more thing to mention is that type 1 type of Chebyshev filters are most commonly used and then these type 2 type of Chebyshev filters. Why? Because the for type 2 type of Chebyshev filters, the ripples exist in the stop band. So once you set actually the stop band limit, that means once you set the stop band attenuation level, what happens after that in the stop band, it does not matter much. So therefore, the Chebyshev filter, the type 1 Chebyshev filters will be most commonly used. Therefore, let's first discuss the design and the details of the type 1 low pass Chebyshev filters. Now, if you see the frequency response of the type 1 Chebyshev filters, this is given by 1 plus epsilon square Tn square x. Now, what is epsilon? Epsilon is a parameter of the filter which is related to the ripple in the passband, ripples in the passband. Tnx is the nth Chebyshev polynomial. What is x? X is the ratio of the analog frequency divided by the analog passband frequency. That means the frequency axis is normalized with respect to the passband frequency. Now Tnx is defined as it's the nth Chebyshev polynomial and is defined as cos of n cos inverse x for mod x less than 1. Mod x less than 1 actually means the omega goes from minus omega p to omega plus omega p, right? Whereas mod x greater than 1 means it goes away from the minus omega p on the negative side and it goes away from the omega p on the positive side. So that means this nth Chebyshev polynomial behaves as a cosine function within minus omega p to plus omega p range, right? What is now if you see this is one side, this is the zero analog frequency and here is the passband. Now let's see the details in the Chebyshev filters. Now this is the zero, this point is corresponds to zero analog frequency. This point corresponds to omega p, capital omega p passband frequency, right? If you consider the negative side of the y-axis also, the same behavior will come there also. So that is why we will find on the negative side also minus omega p. So on the positive side it is omega plus omega p. On the negative side it will be minus omega p. So we will consider the what we are considering in this diagram is that we are considering the frequencies from 0 omega p, omega equal to 0 to omega equal to omega p. All right. Now the if you look at the Chebyshev polynomial closely, from 0 to omega p, capital omega p, since we are considering only the range of this capital omega from 0 to capital omega p, we are not considering in the diagram from 0 to minus omega p, right? So in this range from 0 to omega p, the behavior of the Chebyshev polynomial is cosine function. That means cosine function is an oscillatory function. So because of this oscillatory function, you get the ripples in the passband. All right. And beyond for x mod x greater than 1, that means beyond capital omega p, that means beyond this frequency, beyond this capital omega p, right, the behavior, the function changes to cosh function. Now cosh function is a monotonic function, so therefore the behavior away from the capital omega p is monotonic. So that's what is explained in this nth Chebyshev polynomial function. It says that the function is oscillatory, it's a cosine function ranging from minus omega p to capital omega p, minus capital omega p to plus capital omega p. Whereas beyond that range, right, the function is monotonic from zero. That explains the behavior of type 1 type of Chebyshev filters through this nth Chebyshev polynomial. Now, let us see the characteristics of the Chebyshev polynomial. It says that for mod x less than 1, as I was trying to explain, capital omega varies between minus omega p to capital omega p. Cosine function is oscillatory in nature, which gives rise to oscillations or ripples in the passband. Since magnitude response is an even function, since the magnitude, if you take the magnitude response of this function, you take the mod of this function, it will be an even function. So it suffices to consider capital omega from 0 to capital omega p. So for the magnitude response, since we can consider from 0 to capital omega p. Now when x exceeds 1, that is analog frequency exceeds the passband frequency, cosine function loses its meaning and cos hyperbolic function takes control and is a monotonic function. So that explains the mathematical behavior of this graph basically. Therefore, the ripples in the passband, therefore there will be ripples in the passband only and no the curve will be no ripples in the stopband and the curve will be monotonic in the stopband. So no ripples in the passband and monotonic in the stopband. Okay. The Chebyshev polynomials can be obtained by this recursive equation that we can derive from the Chebyshev polynomial expression given. Now it says that Tn plus 1x is equal to 2x Tnx minus Tn minus 1x for various values of n. Now let's see how this expression is generated from these examples. The first example that I will take is T of n equal to 0 of x when n equal to 0. So in that case, if you see the expression, it is cos of 0 cos inverse x. So this expression inside the bracket will become 0, cos 0 is 1, hence the value is 1 here. For t1x, so let's calculate for t1x, means capital N is 1, so that means cos of cos inverse x. So obviously it will be x only, right? For t2x, given the value of capital N as 2, so this will be cos of twice cos inverse x. So you can take cos inverse x as theta. In that case, this will be the expression for cos 2 theta, which is actually 2 cos square theta minus 1. That means I am if I substitute cos inverse x as theta, so it is 2 cos square theta minus 1, and then we can return back to x only. So this will be 2x square minus 1 for capital N equal to 2. For capital N equal to 3, it will be cos of 3 cos inverse x. So if you solve it further using the trigonometric equation, you will get 4x cube minus 3x. If you compare, if you analyze this expression of T3x, T2x, T1x, and T0x, you will be able to generalize in a generalized way. You will be able to derive this recurrence relation from where we can calculate the Chebyshev polynomial. All right. Now, for capital N odd values, Tn will be equal to 0. That means the magnitude square will be 1. So if you look at this in this graph, when the values of n are odd, in that case, for 0 frequency, for omega equal to 0, the value will be 1. That's what is being said here. For Tnx, x is 0 here. So that means omega starting from 0, the magnitude is 1. But when n values are even, in that case, Tn0 will be equal to 1. Tn0 will be equal to 1. And the magnitude square value for omega equal to 0 will be 1 over 1 plus epsilon square. So now the curve, the ripple starts from 1 over 1 plus epsilon square. In the n odd value, the ripple starts from 1. So that's the difference for odd and even values of capital N. All right. At the passband edge frequency, omega is equal to omega p. We have Tn 1 equal to 1, such that from here we can now at the passband edge frequency omega equal to omega p, we have Tn equal to 1. Fine. From the expression, we can get 1 over under root of 1 plus epsilon square. That means the magnitude value will be equal to 1 minus delta 1, because that's here. This value we say as 1, and this attenuation we make it 1 minus delta 1. So this 1 plus epsilon square under root, this is the this is not as we were actually, this is not j omega square, but this is hj omega. In that case, hj omega equal to 1 over 1 plus epsilon square. This is equal to 1 minus delta 1. Delta 1 is the attenuation starting from 0 dB going downwards. That means if it is a minus 3 dB frequency, so delta 1 will be minus 3 dB. 1 over under root of 1 plus epsilon square is 1 minus delta 1. From here we can calculate, because this will normally be given. For a passband frequency of omega p, we can take it as minus 3 dB also, right? In that case, we can determine the value of epsilon, which is under root of 1 over 1 minus delta 1 whole square minus 1. For this is for capital N equal to capital N odd. That means the magnitude square frequency response Hj omega square oscillates between 1 and 1 over 1 plus epsilon square within the passband. So these are the ripples in the passband, right? And the amplitude of the variation of the ripples go from 1 to 1 over 1 plus epsilon square. And I have already told you the amplitude above the DC value and the amplitude below the DC value both are same. So that is why this is equiripple and has a value 1 over 1 plus epsilon square at omega c or omega p equal to 1, the cutoff frequency. And this is for n values of n to be even. I have already explained it that the ripple will start from 1 over 1 plus epsilon square and then the ripples will be there. The oscillations will be there due to the cos function. And after that, as I said, the cos hyperbolic function will take over and the response will be um, monotonic in the stop band or in the transition band. The poles of a type 1 Chebyshev filter lie on an ellipse in the S-plane. Actually, what we remember that the poles of a Butterworth filter lie on the circle of radius 1 with the center of the circle as the origin of the S-plane. Now, but in the case of Chebyshev type 1 filters, the poles will lie on an ellipse. Now, ellipse will have a major axis and a minor axis. The major axis will be defined by R1 and will be given by omega p beta square plus 1 2 beta divided by 2 beta. I will not derive, I am not deriving these formulas, but since we have to go into the design of Chebyshev filters, so therefore I'm taking the formulas as it is from the literature, and we need to understand actually where the poles lie and where the zeros lie for the case of type 2 filters. This is an all pole filter. Type 1 is a type 1 Chebyshev filter is an all pole filter. All right. So the poles lie on an ellipse in the S-plane with major axis R1 given by this expression and the minor axis R2 is given by uh, omega p beta square minus 1 over 2 beta, where beta we can find out from epsilon values under root of 1 plus epsilon square plus 1 divided by epsilon and the whole nth root, taking the nth root of the whole expression, because beta is related to epsilon according to this equation. All right. Now we can, one thing more is there, we can find the poles from the Butterworth filter also. I mean, if this is an nth order, if we want to find out the poles for an nth order Chebyshev filter, what we can do is, first we will locate the poles for nth order Butterworth filter. Of course, they will lie on the circle of radius R1 or R2 as illustrated in this figure. These are the two circles with radii R1 and R2. All right, and this is actually the ellipse with the major and the minor axis clearly shown. So I was explaining that how we will be able to find out the poles from the Butterworth filter also. So we will, to start with, we will find the pole locations for the Butterworth filter, right? Which they will lie on the circles of radius R1 or R2 as illustrated in the figure. Now, if we denote the angular positions of the poles of the Butterworth filter as phi k equal to pi by 2 plus 2k plus 1 pi by 2n. We derived this formula while we were designing the Butterworth filters. So this is actually the angular positions for the Butterworth filters. Now, if we use this formula, then the positions of the poles for the Chebyshev filter will lie on the ellipse at the coordinates. Now, these will be the coordinates we can actually find out in the rectangle, in the Cartesian coordinate system. So, if you plot these points, so you will see that the poles will lie on an ellipse, right? Where xk The x coordinate will be found out from R2 cos of phi k. R2 is the axis of the minor axis of the ellipse, and yk is R1 sine phi k. So we can directly find from the Butterworth filter also. Phi k we have already got from the Butterworth filter, the position, the angular position of the poles, where k varies from 0 to capital N minus 1 depending on the number of poles. So this is the ellipse, right, where the poles will be, where the locus of the poles will be there. In the Butterworth filter, the locus of the pole was a circle. Now we know that hj omega square, which is the magnitude response, square magnitude response, and we know that it is a monotonic function outside the passband. We know that for type 1 filters, the square magnitude response is monotonic outside the passband, and it is a equiripple behavior inside the passband. Now this outside the passband means going from transition band to stop band, right? Both these bands included. In the passband, it will be ripple behavior. In the transition band and in the stop band, it will be a monotonic behavior. Now we also know this expression at j omega square is equal to 1 over 1 plus epsilon square tn square x, where x is omega by omega b. I have already discussed this normalization of the analog frequency. We can make one approximation, because as omega increases to larger values, in that case this epsilon square tn square x will be very large as compared to 1. So we can approximate it to 1 over epsilon square tn square x. Now taking the square out, so mod of hj omega will be equal to 1 over epsilon tn x. And if we take 20 log of hj omega both sides, 20 log on both sides, so this will be the expression that we'll be able to get after taking the 20 log on both sides. 20 log on both sides. Okay. So when you take 20 log on both sides, then you can, you see here the term is 1 over epsilon over tn x. So you can expand this logarithmic term so that it becomes, because 20 log 1 will be 0, and in that case you will get minus of 20 log epsilon plus 20 log tnx. This whole term is in bracket, and the negative sign will be outside the bracket. Now from the expressions that we, from the recurrence relation that we were deriving for this t and x, if you analyze that recurrence relation for the Chebyshev polynomial, then you can find out that the expression for high values of x, meaning by for larger frequencies, because x is the ratio of omega by omega p. So for large values of x means for larger frequencies, the value of tnx can be approximated to be equal to 2 to the power n minus 1 x to the power n. Now if we replace this tnx by this term, then we can simplify the attenuation expression like minus 20 log hj omega will be equal to 20, because this minus sign will come to this side, that will make it attenuation. So 20 log epsilon e. Because of this log 2, because log 2 constant will come, so that will give it to be 6, that will make it 6. So 6 into capital N minus 1 plus 20 log 20 n log x. So this will be the final expression for the attenuation that you can get in the case of Chebyshev filters. We started from the squared magnitude response, then we approximated it for large values of frequencies. We reached to this point, then we took 20 log, so to put it in the dB scale, and this is our final expression. All right. Now let's have one example which will explain this concept further in a detailed manner. Now we have what we have to do is we have to design a Chebyshev filter. A Chebyshev low pass characteristic is required to have a maximum uh, passband ripple of 1.2 dB and an attenuation of at least 25 dB at x is equal to 2.5. Determine the values of the epsilon and capital N, where x is equal to omega by omega p, right? So we know that this is the square magnitude expression, right? So at x is equal to 1 means because this is the passband frequency. So at x is equal to 1 means omega by omega p is 1. That means this omega is equal to omega p. Now at x is equal to 1, the ripple is 1.2 dB. And t and x, we know that it is 1 from the Chebyshev polynomial. We know that. Once that is the case, so what we do is we put minus 1.2 dB in the expression, right? On the left hand side, equal to 1 over 1 plus epsilon square, we have to calculate the value of epsilon. All right, and t and x, we know it is 1. So after you substitute the values, you will be able to find out 1 over 1 plus epsilon square, right? So because 10 will go to the other side, so that will take it as exponent, and 10 to the power minus 1.2 divided by 10 will be equal to 1 plus epsilon square. And from here, after solving this, you will be able to calculate the value of epsilon. Epsilon will come out to be 0.5641. This is the factor related to the ripple in the passband. All right. Now, in the expression, it is also given that at x is equal to 2.5. That means when this ratio is 2.5, so when this ratio is 2.5, what we can do is in this, namely, it is in the stop band, because that for this 2.5 minus 25 dB will be the attenuation. So in that case, we can use this expression which we derived here for the attenuation. We can use this expression. So it is 25. So we can because we have already calculated epsilon from here, we can substitute the values. If you look at the expression, it is 20 log epsilon plus 6 and 6 into n minus 1 plus 20 l log x. So after you substitute the values and you do the calculation further, you will get capital N to be equal to 2.577. Since we have to take the integer value, next higher integer value, we choose n equal to 3. We choose for this type of filter, we choose the order of the filter to be 3. Now this is the expression that we can, this is the diagram that we can plot. So alpha is the ripple amplitude, right? So ripple amplitude is equal, because this point is 1, this point is 1 plus 1 over 1 plus epsilon square under root. So what is alpha? Alpha will be 1 minus 1 over under root of 1 plus epsilon square. So epsilon we have calculated, and this is going to be 1 tn 0, because at 0 frequency it is 1 here. So in that case, we can determine alpha also. Alpha is 0.129, which is the ripple amplitude, right? We were supposed to find out the values of epsilon and n, right? Epsilon we found out earlier only, and we can find out the values of alpha also, which is the ripple amplitude, which depends on, of course, epsilon. Now it can be shown, though we will not derive it, but it can be shown that a comparison of the normalized Chebyshev pole locations with the normalized Butterworth pole locations reveals that, meaning by if you try to, because when you have a normalized Butterworth filter and you know the pole locations, and now if you compare the Butterworth filter pole locations with the Chebyshev filter pole location in the normalized case, that reveals that the imaginary parts are identical. The imaginary parts of the pole locations are identical. And the real part of the Butterworth pole, if you take the real part of the Butterworth pole, the Chebyshev pole location will be tangent hyperbolic AK times the Butterworth pole location. That's the that. So because the one what how it is useful? It is useful because if you find out the poles using the Butterworth filter design method, the imaginary parts of the pole locations will be same. Now coming to the real part, how you can determine the real part of the Chebyshev filter? You take the real part of Butterworth filter pole in the case of Butterworth filter and multiply with a tangent hyperbolic AK. That will be equal to the real part of the Chebyshev pole, where AK is 1 over sine 1 over n sine hyperbolic inverse of 1 over epsilon. Hence, knowing the normalized Butterworth poles, the corresponding normalized Chebyshev poles can be derived. The denormalized Chebyshev, now this is in the case when you want to determine the normalized Chebyshev poles. Now you can also determine the denormalized Chebyshev poles. That can be done by multiplying the normalized Chebyshev poles by a denormalizing factor, which is equal to cos hyperbolic AK. AK is the same here. In the case you want to denormalize if you want to get the poles, denormalized poles in the case of Chebyshev filters, you can multiply the normalized Chebyshev poles by cos hyperbolic AK. So that's the technique you will have to use to find out the poles in the case of a Chebyshev filter, in the case of a normalized version, or in the case of a denormalized version, right? So that's the design angle for low pass Chebyshev filter. Now this is the recommended design process for deriving HS. If you want to derive the transfer function in the S domain for a Chebyshev low pass filter. Now, first of all, you will have to find out, you will have to obtain values for epsilon and n, right? You can use this expression. Then obtain the normalized Butterworth poles. All right. Select only the poles in the left-hand side of the S-plane because that will determine the stability, because that will lead to a stable system. Obtain corresponding normalized Chebyshev poles. Then you will multiply real parts of the poles by tangent hyperbolic, so you will be able to get the normalized poles. All right, this expression I'm just giving you as it is because we will not derive that. From here you will determine the epsilon and or you will use the method as we used in our example and multiply the real parts of the poles by tangent hyperbolic. Then obtain the denormalized Chebyshev poles. How you will be able to get the denormalized poles? By multiplying the poles real and imaginary by cos hyperbolic AK. Right. So you will denormalize the poles by multiplying the poles of the normalized Chebyshev filter by cos hyperbolic AK. From here, you will obtain the values of k, that will be a constant, right? And from there, you will be finally getting the transfer function of the Chebyshev filter. All right. Then I told you that the difference between the type 1 and type 2 Chebyshev filters is that the ripples are there in the passband and response is monotonic in the stop band for the case of type 1 filters. The case of type 2 Chebyshev filters is just the reverse of that, meaning by the frequency response of the filter is monotonic in the passband, whereas there will be equi ripple behavior in the stop band. All right. So these are not used very much in the practical cases, but we will look at the expression of the frequency of the magnitude response, square magnitude response, and we will see the locations of zeros, right? A type 2 Chebyshev filter contains zeros as well as poles. The magnitude squared of its frequency response is given by this expression, where Tn, as usual, is the Chebyshev polynomial, and it is given by omega s by omega p, where omega s is the stop band frequency and omega p is the pass band frequency. Where Tnx is the nth order Chebyshev polynomial. As we know already, we have gone through the type 1 design. Omega s is the stop band frequency. The zeros of the type 2 Chebyshev filter are located on the imaginary axis at these points. So the points will be given by j into omega s divided by sine phi k, where k varies from 0 to n minus 1, and phi k we have already seen for the case of Butterworth filters. Butterworth filter design, the angular position of the poles in the Butterworth case. Right, the same will be used for getting the zeros for the type 2 Chebyshev filter. Now, this is the response of the Chebyshev filter for the case of n odd or n even. Clear? The pole locations can also be found out with the coordinates as Vk and Wk. So Vk expression is omega s into xk divided by xk square plus yk square. K again varies from 0 to capital N minus 1, and Wk is omega s into yk divided by xk square plus yk square. So beta is related to the ripple in the stop band through the equation. So you will be able to get beta from here. Delta 2 is the attenuation for the stop band attenuation, right? And this is the expression. I'm not again deriving this expression. I'm straightway giving this expression to find out the order of the filter. Now, from this description, we observe that the Chebyshev filters are characterized by the parameters n, epsilon, delta 2, and the ratio omega s by omega p. For a given set of specifications on epsilon, delta 2, omega s by omega p, we can determine the order of the filter from this equation. Let's take the equation as it is, and we can find out the order of the filter, right? Where by definition, delta 2 is equal to 1 over under root of 1 plus delta square. With this, I finish with the design of Chebyshev filters, type 1 and type 2 Chebyshev filters, right? We will continue with the subject in the next lecture. Thank you.